My dear students, welcome back to our channel. Students, in this video I am explaining MBA first semester. Subject Statistics for Management. Important long questions and answers. Let's start quick revision. First unit. First important long question is: explain the managerial applications of statistics. Managerial applications of statistics are essential for making informed, data-driven decisions in business. By using statistical tools, managers can analyze data, evaluate performance, forecast trends, and improve efficiency. Here's how statistics are applied in management. 1. Decision-making. Statistics help managers make decisions based on actual data rather than intuition. For example, a manager in a retail store can analyze sales data to predict future demand. By using moving averages or regression analysis, the manager can forecast how much stock to order, reducing the risk of overstocking or running out of products. 2. Quality control. In manufacturing, managers use statistical tools like control charts to monitor production quality. If the number of defective products exceeds an acceptable threshold, corrective actions can be taken. For instance, a factory producing electronics might use statistical sampling to check product quality, ensuring that only the best products reach customers. 3. Market research. Statistics play a crucial role in understanding consumer behavior and market trends. Managers conduct surveys and analyze data to understand customer preferences, satisfaction, and purchasing habits. For example, a fast food chain may conduct a survey on customer preferences for new menu items and use statistical analysis to determine the most popular choices, helping to guide product development. 4. Forecasting. Statistical techniques like regression analysis help managers predict future outcomes based on historical data. For instance, a sales manager might use data from previous years to predict next quarter's sales, helping them to plan inventory levels, staffing, and budget. 5. Risk management. Managers use statistical methods to assess and manage risks. For example, in finance, a manager may use probability theory to evaluate the risk of investments or assess the likelihood of different financial scenarios. This helps to make better, data-backed decisions when handling resources. 6. Performance evaluation. Statistical tools help managers assess employee performance. For example, a sales manager might analyze sales data to identify top performers, set realistic targets, and provide feedback to improve the overall sales team's performance. In conclusion, statistics help managers make more accurate, data-informed decisions, optimize resources, improve product quality, and predict future trends. By applying statistical methods, managers can enhance productivity, minimize risks, and maintain a competitive advantage in the market. Next important long question is: explain addition and multiplication theorems on probability. The addition and multiplication theorems in probability are fundamental rules used to calculate the likelihood of different events happening. Here's an easy-to-understand explanation of both. 1. Addition theorem of probability. The addition theorem helps us calculate the probability of either one event or another happening. It's used when we are interested in the probability that at least one of two events will occur. Formula: where PAB is the probability that either event A or event B happens. PAB is the probability that both events A and B happen together. Example, suppose you roll a fair six-sided die. Let's define two events. Event A, rolling an even number 2, 4, 6. Event B, rolling a number greater than 3, 4, 5, 6. The probability of rolling an even number P, A, is 3/6 and the probability of rolling a number greater than 3P, B, is 3/6. The overlap, both even and greater than 3, is the number 4 and 6, so PAB is equal to 2/6. Using the addition rule, PAB is equal to 3. Thus, the probability of either rolling an even number or a number greater than 3 is 2/3. 2. Multiplication theorem of probability. The multiplication theorem helps us calculate the probability of both events A and B happening together. It's used when we want to find the probability of two independent events happening at the same time. Formula for independent events. Example, suppose you roll a fair die and flip a fair coin. Let's define two events. Event A, rolling a number greater than 3, 4, 5, 6. Event B, getting a heads on the coin flip. The probability of rolling a number greater than 3P, A, is 3/6 and the probability of flipping heads P, B, is a half. Since the roll of the die and the coin flip are independent, we use the multiplication rule. PAB 1, 4. Thus, the probability of rolling a number greater than 3 and flipping heads is a quarter. Conclusion. The addition theorem helps find the probability of at least one event happening and accounts for overlapping events. The multiplication theorem is used to calculate the probability of both events happening together, particularly for independent events. Both rules are essential for solving probability problems and understanding how different events relate to each other. Next important long question is: a husband and wife appear in an interview for two vacancies in the same post. The probability of husband's selections is 1/7 and that of wife's selection is 1/5. What is the probability that both of them will be selected? 2. Only one of them will be selected. And 3. None of them will be selected. To solve this problem, we can use basic probability rules. Let's break it down step by step. Given probability of the husband's selection P, H, is equal to 1/7. Probability of the wife's selection P, W, is equal to 1/5. Since the selection of the husband and wife are independent events, we can calculate the required probabilities as follows. Both of them will be selected. The probability that both the husband and wife are selected is simply the product of their individual probabilities. P, both selected, is equal to P, H, times P, W, is equal to 1/35. So, the probability that both of them will be selected is 1/35. 2. Only one of them will be selected. For only one of them to be selected, two cases can happen. 1. The husband is selected and the wife is not selected. 2. The wife is selected and the husband is not selected. Probability that the husband is selected and the wife is not P, H and not W is equal to 4/35. Probability that the wife is selected and the husband is not P, W and not H is equal to 6/35. Now, we sum these probabilities to find the total probability of only one of them. being selected. P, only one selected, is equal to 2 sevenths. So, the probability that only one of them will be selected is 2 sevenths. 3, none of them will be selected. The probability that neither of them is selected is the product of the probabilities that both are not selected. Probability that the husband is not selected 1p, h, is equal to 6 sevenths. Probability that the wife is not selected 1p, w, is equal to 4 fifths. So, the probability that neither is selected is p, none selected, is equal to 24/35. So, the probability that neither of them will be selected is 24/35. Final answers. Probability that both will be selected, 1/35. 2. Probability that only one will be selected, 2 sevenths. 3. Probability that none will be selected, 24/35. Next important long question is: from the following data of age of employees, calculate coefficient of skewness and comment on the result. To calculate the coefficient of skewness, we need to use the Bowley's coefficient of skewness formula, which is a simple measure of skewness based on quartiles. However, in this case, we have grouped data, so we'll need to first calculate the mean, median, and standard deviation of the data. Step 1. Calculate the mean. We need to first calculate the midpoint of each class, and then use the formula for the mean of grouped data. Midpoint calculation. The midpoint of each class can be calculated as midpoint is equal to lower class limit plus upper class limit 2. We are given the cumulative frequency, so the midpoint for each class interval will be: for age 25, midpoint is equal to 12.5. For age 55, midpoint is equal to 2.5. Frequency. Total frequency N. N is equal to 405. Total of Fx. Fx is equal to 18,447.5. Mean. The mean, x, can be calculated as x is equal to 45.5 years. Step 2. Find the median. The median is the middle value when the data is ordered. Since we are working with grouped data, we need to locate the median class, which corresponds to the cumulative frequency just greater than n/2. 405 by 2 is equal to 202.5. The cumulative frequency just greater than 202.5 is 240 from the class interval 40 to 45. Thus, the median lies in the class interval 40-45. Now, we can calculate the exact median using the formula for grouped data. Median is equal to 44.84. Thus, the median is approximately 44.84 years. Step 3. Find the mode. We will calculate the mode using the formula for grouped data. Mode is equal to 50. Thus, the mode is 50 years. Step 4. Calculate skewness. We can now calculate the coefficient of skewness using the formula. After calculating these values, we find the sum of squared deviations and calculate the standard deviation. Finally, use the formula for skewness once the standard deviation is found. Conclusion. Once the calculations are completed for skewness, we can interpret the result. If skewness is positive, the data is skewed to the right, tail on the right. Negative, the data is skewed to the left, tail on the left. 0, the data is symmetrically distributed. Next important long question is: Naran has 2 bags. Bag 1 have 7 red and 2 blue balls, and bag 2 have 5 red and 9 blue balls. Narun draws a ball at random and it turns out to be red. Determine the probability that the ball was from the bag 1 using the Bayes theorem. To solve this problem, we can apply Bayes theorem. Bayes theorem allows us to calculate the probability of an event occurring given some prior knowledge of related events. Problem breakdown. Bag 1 has 7 red and 2 blue balls. Bag 2 has 5 red and 9 blue balls. Naran draws a red ball. We need to determine the probability that the red ball came from bag 1. Let a 1 is equal to the event that the ball was drawn from bag 1. A 2 is equal to the event that the ball was drawn from bag 2. R is equal to the event that the ball drawn is red. We need to find P, A1 vertical bar R, the probability that the ball came from bag 1 given that it is red. Bayes theorem states P A1 R is equal to P RA1 P A1 P R, where P RA1 is equal to probability of drawing a red ball from bag 1. P A1 is equal to probability of selecting bag 1. P R is equal to total probability of drawing a red ball. Step 1. Calculate the probabilities. 1. P A1 and P A2 since there is no preference mentioned for selecting between the two bags, we assume that each bag is equally likely to be chosen, so P A1 is equal to P A2 is equal to a half. 2 P RA1 this is the probability of drawing a red ball from bag 1. Since bag 1 contains 7 red and 2 blue balls, the probability of drawing a red ball is P RA1 is equal to 7, 7 plus 2 is equal to 7 9. 3 P RA2 this is the probability of drawing a red ball from bag 2. Since bag 2 contains 5 red and 9 blue balls, the probability of drawing a red ball is P RA2 is equal to 5, 5 plus 9 is equal to 5 14. 4 P R this is the total probability of drawing a red ball, considering both bags. We use the law of total probability. P R is equal to P RA1 P A1 plus P RA2 P A2. Substitute the values. P R is equal to 47/63. Step 2. Apply Bayes theorem. Now, use Bayes theorem to calculate P A1 R. P A1 R is equal to 49/94. Final answer. The probability that the red ball was from bag 1 is 49/94 or approximately 0.520, 52.0%. Next, second unit. Second unit. First important long question is, what is random variable? What are the different types of random variable? What is a random variable? A random variable is a numerical outcome of a random event or experiment. It represents the result of a process where the outcome cannot be predicted with certainty. The value of a random variable is determined by chance and it can take different values depending on the situation. For example, if you roll a dice, the outcome 1, 2, 3, 4, 5, or 6 is a random variable, because you can't predict exactly which number will appear on the dice. If you flip a coin, the random variable could be heads or tails. Types of random variables. There are two main types of random variables, discrete and continuous. 1. Discrete random variable. A discrete random variable can only take a finite or countably infinite number of values. These values are usually whole numbers or integers. Example: the number of cars in a parking lot, you can have 0, 1, 2, 3, etc., but not 1.5 cars. The number of heads you get when flipping 3 coins, it can be 0, 1, 2, or 3 heads, but not a fraction of a head. Key point: the values are distinct and separate. 2. Continuous random variable. A continuous random variable can take any value within a given range or interval. These variables can take on infinitely many values, often involving real numbers. Example: the height of a person, which can be any value like 5.5 feet, 5.75 feet, or 5.784 feet. The time it takes for a car to complete a race, which could be 30.5 seconds, 30.55 seconds, etc. Key point: the values can be infinitely detailed and measured. Conclusion: a random variable is essential in statistics and probability theory because it helps to quantify the outcomes of random events. Understanding the difference between discrete and continuous random variables is important because the methods of analyzing them differ. Discrete variables are countable, while continuous variables can take any value within a given range. Next important long question is: explain the types of probability distributions with real-time examples. Types of probability distributions. Probability distributions describe how the probabilities of different outcomes are spread across the possible values of a random variable. There are two main types of probability distributions: discrete probability distributions and continuous probability distributions. Let's explore each type with real-time examples. 1. Discrete probability distribution. A discrete probability distribution applies to random variables that can take on a finite or countably infinite number of distinct values. Example: binomial distribution. In a binomial distribution, there are two possible outcomes for each trial: success or failure. It's useful when the trials are independent and there's a fixed number of trials. Example: a company tests a product 10 times, and the probability of success, a product passing the test, is 0.7. The binomial distribution helps calculate the probability of passing a specific number of tests. Example: exactly 7 passes out of 10. Another example: Pearson distribution. The Pearson distribution models the number of times an event occurs in a fixed interval of time or space. It is used when events happen independently and at a constant rate. Example: a call center receives 5 calls per minute on average. The Pearson distribution can be used to determine the probability that exactly 3 calls will arrive in a given minute. 2. Continuous probability distribution. A continuous probability distribution applies to random variables that can take any value within a given range, infinite values. These distributions are used for measurements. Example: normal distribution. The normal distribution, also called the Gaussian distribution, is a bell-shaped curve that describes how data tends to cluster around a central value. Most real-world measurements follow a normal distribution. Example: the height of people in a population often follows a normal distribution. If the average height of men in a country is 5'10" with a standard deviation of 2 inches, the normal distribution can estimate the probability of a person's height falling within a specific range, say between 5, 8 and 6. Another example, uniform distribution. The uniform distribution is used when every value in a given range has an equal probability of occurring. Example, if a store sells a product with a price range of $10 to $20 and each price point between $10 and $20 is equally likely, then the price follows a uniform distribution. Conclusion. Probability distributions are crucial in statistics to model and analyze random events. Discrete distributions like the binomial and Pearson are used for countable events, while continuous distributions like the normal and uniform distribution are used for measurements. Both types help businesses, researchers, and analysts make predictions and decisions based on uncertain outcomes. Next important long question is: find the probability of getting at least 5 times head-on tossing and unbiased coin for 6 times by using the binomial distribution. To solve this problem, we can use the binomial distribution formula. The binomial distribution describes the probability of getting exactly k successes, in this case, heads, in n independent trials, in this case, coin tosses, given the probability p of success on each trial. The formula for binomial distribution is where n is equal to number of trials, coin tosses, is equal to 6. K is equal to number of heads. We will calculate for k is equal to 5 and 6. P is equal to probability of getting a head on each toss is equal to 0.5 since the coin is unbiased. Nk is equal to binomial coefficient calculated as. We are asked to find the probability of getting at least 5 heads, which means we need to calculate P x greater than or equal to 5 is equal to P x is equal to 5 plus P x is equal to 6. Step 1. Calculate P x is equal to 5. Using the binomial formula, P x is equal to 5 is equal to 332. Step 2. Calculate P x is equal to 6. Using the binomial formula again, P x is equal to 6 is equal to 1/64. Step 3. Calculate the total probability. P x greater than or equal to 5 is equal to 7/64. Final answer. The probability of getting at least 5 heads when tossing an unbiased coin 6 times is 7/64, which is approximately 0.1094 or 10.94%. Next important long question is: the speeds of cars are measured using a radar unit on a motorway. The speeds are normally distributed with a mean of 90 km per hour and a standard deviation of 10 km per hour. What is the probability that a CR selected at chance is moving at more than 100 km per hour? To find the probability that a car selected at random is moving at more than 100 km per hour, we can use the normal distribution. Given mean speed, mu, is equal to 90 km per hour. Standard deviation, sigma, is equal to 10 km per hour. We need to find the probability that the speed x is greater than 100 km per hour. Step 1. Standardize the value using the z-score formula. The z-score formula is where x is the value we are interested in, 100 km per hour. Mu is the mean, 90 km per hour. Sigma is the standard deviation, 10 km per hour. Substituting the values, z is equal to 1. So, the z-score corresponding to 100 km per hour is 1. Step 2. Use the z-score to find the probability. To find the probability that a car is moving at more than 100 km per hour, we need to calculate the area to the right of Z is equal to 1 under the standard normal distribution curve. Using the standard normal distribution table or a calculator, we find the cumulative probability corresponding to Z is equal to 1. This represents the probability that a car is moving at less than 100 km per hour. To find the probability that a car is moving more than 100 km per hour, we subtract this value from 1. P x 100 is equal to 0.1587. Final answer. The probability that a car selected at random is moving at more than 100 km per hour is approximately 0.1587 or 15.87%. Next, third unit. Third unit. First important long question is, what are the main objectives of sampling, and also discuss the different types of sampling methods? Main objectives of sampling. Sampling refers to the process of selecting a small group or subset from a larger population to make inferences about the entire population. The main objectives of sampling are: 1. Cost-effective. It allows researchers to collect data from a smaller, manageable group rather than the entire population, saving time and money. 2. Time-saving. Collecting data from a sample is quicker than gathering information from every member of a large population. 3. Accuracy. A well-chosen sample can provide accurate insights about the population, avoiding unnecessary data collection. 4. Feasibility. Sometimes, it's not practical to study the entire population due to size, accessibility, or other limitations, so a sample is used instead. Different types of sampling methods. 1. Probability sampling. Every individual has a known chance of being selected. Simple random sampling. Every member of the population has an equal chance of being selected. For example, drawing names from a hat to choose 5 people from a group of 50. Stratified sampling. The population is divided into groups, strata, based on a specific characteristic, example, age, gender, and then random samples are taken from each group. For example, a school might divide students into age groups and randomly select from each group. Systematic sampling. Every nth member of the population is selected. For example, selecting every 10th person on a list of 100 people. 2. Non-probability sampling. Not every individual has a known chance of being selected. Convenience sampling. The sample is chosen based on what's easiest or most convenient. For example, surveying the first 10 people you meet in a mall. Judgmental, purposive sampling. The researcher selects individuals based on their knowledge or judgment about who would provide the best information. For example, interviewing experts in a field to gain detailed insights. Snowball sampling. This method is used when the population is hard to reach. One participant helps identify others, who are then recruited for the study. For example, researching a specific group, like members of a rare hobby community, where one participant leads to others. In conclusion, sampling is crucial for efficient data collection, and understanding the different types helps researchers choose the best approach for their studies. Each method has its pros and cons depending on the research goals and available resources. Next important long question is: write a detailed note on non-random sampling methods with suitable examples. Non-random sampling methods. Non-random sampling methods refer to techniques where the individuals or units in a sample are not selected by random chance. Instead, researchers choose them based on certain criteria, convenience, or judgment. These methods are often easier and faster to carry out, but they can lead to biased results since not everyone in the population has an equal chance of being selected. Here are some common non-random sampling methods. 1. Convenience sampling. This is the simplest method where the researcher selects participants based on their availability or easy access. For example, a researcher might survey people in a nearby shopping mall simply because it's easy to reach them. Example, a student surveys their classmates about study habits only because they are easily accessible in the classroom. Limitations: this method can be biased since it only includes people who are easy to reach, not necessarily representing the entire population. 2. Judgmental, purposive sampling. In this method, the researcher uses their judgment to choose participants who they believe will provide the most relevant or useful information for the study. Example, a researcher studying how technology affects education might select expert teachers or school administrators who have in-depth knowledge of this topic. Limitations: since it's based on the researcher's judgment, the sample might not be representative, leading to potential bias. 3. Snowball sampling. This technique is often used when studying populations that are hard to access. The researcher starts with a small group of individuals and asks them to refer others who are similar to them. The process continues as more people are added. Example, a researcher studying drug users may start with a few known participants and ask them to introduce others who fit the same criteria. Limitations: snowball sampling can create a sample that is not diverse, as participants may all have similar characteristics or experiences. In conclusion, non-random sampling methods can be useful in certain situations, especially when resources are limited or when studying specific groups. However, these methods can lead to biased results, and the findings may not be generalizable to the entire population. Researchers need to carefully consider the trade-offs when choosing a sampling method. Next important long question is: what is hypothesis, and explain its types with suitable examples? What is a hypothesis? A hypothesis is a statement or an educated guess about the relationship between two or more variables that can be tested through research and experiments. It is a starting point for scientific inquiry that helps researchers focus their study and predict outcomes. A hypothesis is typically made before conducting a study and is tested using data. Based on the results, the hypothesis can be either accepted or rejected. Types of hypotheses. 1. Null hypothesis, H. The null hypothesis suggests that there is no significant relationship or effect between the variables being studied. It assumes that any observed differences are due to chance. Example, if a researcher wants to know if a new teaching method improves student performance, the null hypothesis might state, there is no difference in student performance between the new teaching method and the traditional method. 2. Alternative hypothesis, H. The alternative hypothesis contradicts the null hypothesis and suggests that there is a significant relationship or effect. It proposes that the research findings are not due to chance. Example, in the same study on teaching methods, the alternative hypothesis could be, the new teaching method improves student performance compared to the traditional method. 3. Directional hypothesis. A directional hypothesis predicts the specific direction of the relationship between variables, meaning it specifies whether the effect will be positive or negative. Example, if a researcher believes that more hours of study will lead to better exam scores, the directional hypothesis might state, increased study hours lead to higher exam scores. 4. Non-directional hypothesis. A non-directional hypothesis predicts a relationship between variables, but it doesn't specify the direction of the relationship, whether it will be positive or negative. Example, a non-directional hypothesis could be, there is a relationship between study hours and exam scores. It doesn't specify whether more study hours will result in higher or lower scores, just that there is some relationship. Conclusion. In summary, hypotheses are essential for guiding research and experiments. They provide a basis for testing and help researchers make predictions. The types of hypotheses, such as null, alternative, directional, and non-directional, help shape the direction of a study and determine how data will be interpreted. Next important long question is: XYZ, a tea manufacturing company, is interested in determining the consumption rate of tea per household in Hyderabad. The management believes that yearly consumption per household is normally distributed. To determine the consumption rate of tea per household in Hyderabad, XYZ tea manufacturing company would need to conduct a study using statistical methods to gather data on the average yearly tea consumption. Since the management believes that yearly consumption per household follows a normal distribution, they can use this assumption to guide their sampling and analysis. Here's how XYZ tea manufacturing company can proceed. 1. Define the population and sample. The population is all households in Hyderabad. The sample will be a representative group of households selected from Hyderabad for data collection. 2. Sampling method. Since the company believes the consumption rate is normally distributed, they could use random sampling to select households. This helps ensure that the sample is representative and eliminates biases. Example, the company can randomly select 200 households from different areas of Hyderabad. This will give a diverse sample that could reflect the consumption patterns across the city. 3. Data collection. The company can collect data by asking the selected households about their yearly tea consumption. This can be done via surveys, interviews, or questionnaires, where respondents report how much tea they consume annually. Example question: how many kilograms of tea does your household consume in 1 year? 4. Testing the assumption, normal distribution. The company believes that tea consumption is normally distributed. Once the data is collected, they can analyze it using statistical tests, example, the Shapiro-Wilk test, to confirm whether the data follows a normal distribution. Example, if the data shows a bell-shaped curve when plotted, this would confirm the assumption that consumption follows a normal distribution. 5. Analysis of results. After confirming the normal distribution, the company can calculate the mean and standard deviation of the tea consumption data. These values will give insights into the average consumption and the variability of tea consumption across households. Example, if the average consumption, mean, is 10 kilograms per year and the standard deviation is 2 kilograms, this means that most households consume between 8 and 12 kilograms per year, with a few outliers above or below that range. 6. Conclusion and decision. The company can use these results to make strategic decisions, such as adjusting their production levels, marketing strategies, or targeting specific households based on consumption patterns. In summary, by conducting a random sample survey and analyzing the data for normal distribution, XYZ tea manufacturing company can estimate the average yearly tea consumption per household in Hyderabad. This helps them understand their market better and make informed decisions. Next, fourth unit. Fourth unit. First important long question is: discuss at length the applications of chi-square and ANOVA. Applications of chi-square test and ANOVA. Chi-square test. The chi-square, chi superscript 2, test is a statistical test used to determine whether there is a significant association between categorical variables. It compares the expected frequencies, what we would expect to happen, to the observed frequencies, what we actually observe. It is commonly used in goodness of fit tests and test of independence. 1. Goodness of fit test. Used to check if a sample matches the expected distribution. Example, a company wants to know if the colors of cars sold, red, blue, green, follow a 2:3:5 ratio. They collect data on the actual number of cars sold and compare it to the expected ratio using a chi-square test. 2. Test of independence. Used to determine if two categorical variables are independent or related. Example, a researcher wants to know if there is an association between gender, male, female, and preference for a certain type of product, product A, product B. By using the chi-square test, they can see if gender influences product preference. ANOVA analysis of variance. ANOVA is a statistical method used to compare the means of 3 or more groups to see if there is a significant difference between them. It tests the hypothesis that all group means are equal. 1. One-way ANOVA. Used when you have one independent variable with 3 or more groups and want to compare the means. Example, a teacher wants to compare the test scores of students in 3 different teaching methods, Method A, Method B, Method C. By using one-way ANOVA, the teacher can determine if the test scores differ significantly between the methods. 2. Two-way ANOVA. Used when there are 2 independent variables, and you want to see their individual and combined effects on a dependent variable. Example, a company tests the effect of 2 factors, training type, online, in-person, and work hours, part-time, full-time, on employee performance. Two-way ANOVA helps determine if these factors affect performance and if there's an interaction between them. Conclusion. Both chi-square and ANOVA are essential tools in statistics. The chi-square test is perfect for categorical data and determining relationships, while ANOVA is used to compare group means in continuous data. Understanding when and how to apply each of these tests is crucial for making informed decisions in research, business, and many other fields. Next important long question is: in an experiment to study whether smoking affects health, the following data were collected. Test the hypothesis that smoking does not affect health. To test the hypothesis that smoking does not affect health, we can use the chi-square test of independence. This test helps determine whether two categorical variables, in this case, smoking level and health effect, are related or independent. Step 1. Set up the hypotheses. Null hypothesis: H. Smoking does not affect health. In other words, there is no association between smoking levels and health status. Alternative hypothesis: H. Smoking affects health. There is an association between smoking levels and health status. Step 2. Construct the contingency table. Step 3. Calculate the expected frequencies. The expected frequency for each cell is calculated using the formula E is equal to 40. Similarly, we calculate the expected frequencies for all cells. Step 4. Calculate the chi-square statistic. The formula for the chi-square statistic is where O is equal to observed frequency, E is equal to expected frequency. Now, let's compute the chi-square value for each cell. 1. For health affected and light smoking is equal to 14.4. 2. For health affected and moderate smoking equals 3.025. 3. For health affected and heavy smoking. Now, sum all the chi-square values. Chi2 is equal to 32.8. Step 5. Determine the degrees of freedom, df. The degrees of freedom for a chi-square test of independence is calculated using the formula, where R is equal to number of rows, 2, for health affected and not affected. C is equal to number of columns, 3, for light, moderate, and heavy smoking. Thus, df is equal to equals 2. Step 6. Find the critical value. At a 5% significance level, alpha is equal to 0.05 and 2 degrees of freedom. The critical value from the chi-square distribution table is approximately 5.99. Step 7. Compare the chi-square statistic with the critical value. Chi-square statistic 32.8 is greater than the critical value 5.99. Step 8. Conclusion. Since the chi-square statistic 32.8 is greater than the critical value 5.99, we reject the null hypothesis. This means there is a significant association between smoking levels and health status. Smoking does affect health. Next important long question is: the following table gives the yields on 15 sample plots under 3 varieties of seeds. To test if there is a significant difference in the yields of the 3 seed varieties A, B, and C, we can perform a one-way analysis of variance, ANOVA. ANOVA helps determine if there are any statistically significant differences between the means of 3 or more independent groups. Step 1. Set up the hypotheses. Null hypothesis: H. The means of the 3 seed varieties are equal. That is, the average yield of seed varieties A, B, and C are the same. H0, mu A is equal to mu B is equal to mu C. Alternative hypothesis: H. At least one of the means is different. That is, the average yield of at least one of the seed varieties is different from the others. H1, at least one mu I is different. Step 2. Organize the data. Here's the data you provided. Step 3. Calculate the overall mean. The overall mean, grand mean, is the mean of all the observations. Grand mean is equal to sum of all values total number of observations. We will calculate the sum of all the values and then divide by the total number of observations, 15. Step 4. Calculate the sum of squares. 1. Total sum of squares, SST. This measures the total variation in the data. SST is equal to sigma, xij grand mean, 2. 2. Sum of squares between groups, SSB. This measures the variation between the group means and the overall mean. SSB is equal to ni, group meani grand mean, 2. Where ni is the number of observations in group I. 3. Sum of squares within groups, SSW. This measures the variation within each group. Step 5. Compute the F statistic. The F statistic is calculated using degrees of freedom. df between groups is equal to K1, where K is the number of groups, in this case, 3. df within groups is equal to Nk, where N is the total number of observations, in this case, 15. Finally, we compare the F statistic with the critical value from the F distribution table at a 5% significance level, and df1 is equal to 2 and df2 is equal to 12. Next, fifth unit. Fifth unit. First important long question is: what is correlation? What are its business applications? What is correlation? Correlation is a statistical measure that shows the relationship or connection between two or more variables. It tells us how changes in one variable are associated with changes in another. If two variables tend to increase or decrease together, they are said to have a positive correlation. If one variable increases while the other decreases, they have a negative correlation. If there's no predictable relationship between the two, the correlation is zero or no correlation. Correlation is measured on a scale from -1 to +1. +1 means a perfect positive correlation. 1 means a perfect negative correlation. 0 means no correlation. Example of correlation. Imagine a business analyzing the relationship between advertising spending and sales revenue. If increasing advertising leads to higher sales, there is a positive correlation. Conversely, if more advertising leads to lower sales, perhaps due to ineffective campaigns, the correlation would be negative. Business applications of correlation. 1. Sales and advertising. Businesses often use correlation to understand how advertising budgets impact sales. If a company finds a strong positive correlation between ad spending and sales, they can allocate more resources to advertising campaigns to boost sales. 2. Customer satisfaction and loyalty. A business might analyze the correlation between customer satisfaction scores and repeat purchases. If they find a strong positive correlation, improving customer satisfaction could lead to increased customer loyalty and higher sales. 3. Stock market and economic indicators. Companies and investors use correlation to assess how economic indicators, like inflation or unemployment, affect stock market performance. If there's a negative correlation between stock prices and interest rates, businesses might adjust their investment strategies based on interest rate forecasts. 4. Inventory management. Businesses can analyze the correlation between customer demand for certain products and inventory levels. A positive correlation could help businesses predict and manage stock levels to meet demand efficiently. Conclusion. In business, understanding correlation helps companies make informed decisions, optimize strategies, and improve performance. By knowing how different factors are related, businesses can plan more effectively, whether it's managing resources, setting prices, or investing in marketing. Next important long question is: 10 competitors in a beauty contest are ranked by 3 judges in the following order. Use the rank correlation coefficient to determine which pair of judges has the nearest approach to common tastes in beauty. To determine which pair of judges has the nearest approach to common tastes in beauty, we will use Spearman's rank correlation coefficient. This method helps to measure the strength and direction of the relationship between two rankings. Spearman's rank correlation coefficient formula. The formula for Spearman's rank correlation coefficient, denoted as RS, is where N is equal to number of observations, in this case, 10 competitors. D is equal to difference between the ranks of corresponding values from two judges. Sigma D2 is equal to sum of the squared differences between the ranks. Step 1. Organize the data. Here are the rankings for the 3 judges. Step 2. Calculate the differences, D, between ranks. For Judge I and Judge 2, Sigma D2 is equal to 227. For Judge I and Judge 3, Sigma D2 is equal to 213. Step 3. Calculate the rank correlation coefficient, R. For Judge I and Judge 2, equal to 0.375. For Judge I and Judge 3, equal to 0.435. For Judge 2 and Judge 3, is equal to 0.29. Step 4. Conclusion. The correlation coefficient between judge I and judge 2 is minus 0.375, which indicates a weak negative correlation. The correlation coefficient between judge I and judge 3 is 0.435, which indicates a moderate positive correlation. The correlation coefficient between judge 2 and judge 3 is minus 0.29, which also indicates a weak negative correlation. Based on these results, judge I and judge 3 have the nearest approach to common tastes in beauty, as they have the highest positive correlation coefficient, 0.435. Next important long question is: find the Pearson's coefficient of correlation between price and demand from the following data. To find Pearson's coefficient of correlation between price and demand, we use the following formula, where R is equal to Pearson's correlation coefficient, N is equal to number of data points, X is equal to price values, Y is equal to demand values, Sigma X is equal to sum of all the price values, Sigma Y is equal to sum of all the demand values, Sigma XY is equal to sum of the products of corresponding price and demand values. Sigma X2 is equal to sum of the squares of the price values. Sigma Y2 is equal to sum of the squares of the demand values. Step 1. Organize the data. Step 2. Calculate the required sums. Step 3. Substitute values into the formula. Now, we can substitute these values into the Pearson's correlation formula. R is equal to R0.312. Conclusion. The Pearson's correlation coefficient between price and demand is approximately minus 0.312, which indicates a moderate negative correlation. This means that as the price increases, the demand tends to decrease, but the relationship is not very strong.